Hello, my name is Chaitani.
And my name is Gabby, and we work in Dr. Alvarez's lab here at the University of Cincinnati. And today we're going to talk to you about the biological applications of carbon nanotubes. Here in the Alvarez lab, we work with carbon nanotubes, which are cylindrical in shape and are made out of carbon atoms. These CNTs are grown on a plate that we call a substrate, and they grow from a catalyst, which is sort of like a seed. So they're going to grow up from that catalyst when we add in different gases and heat, which act as the nutrients. So the CNTs grow up from the substrate like blades of grass coming out of the ground. And in the Alvarez lab, we use a specific kind that are called spinnable arrays, so we're able to pull them out, which I'll show next. Okay, so you just watched a short video on the synthesis of carbon nanotubes, or how we make the carbon nanotubes. So now we're going to look at an actual CNT array that we use in the lab. So again, the carbon nanotubes are going to grow up like blades of grass. So even though it looks really densely packed, there's still space in between the tubes. So what we can do with these, because like I said in the video, they're spinnable, we're able to draw the CNTs out in order to put them into different formations. So we can have something like this, which is a ribbon of CNTs, or we can start applying a twisting motion to the CNT array, and we use a motor to do this normally. And that twisting motion makes the array turn into more of a fiber. So if you think of like a piece of thread that's used in clothing.
My friend Gabby talked to you about carbon nanotubes. Now you already know what carbon nanotubes are. In Alvarez lab, we study how carbon nanotubes can be used to develop implants to treat illnesses caused by damage in your brain and organs. Before going to talk about all these things, let's learn about how our brain works. In healthy people, all sensations, thoughts, and memories, and feelings, and all the movements are result in signals that controlled by the brain. Have you ever wondered how brain can do that? There are cells called neurons in our brain. There are billions of them, so they can pass these messages from our brain to organs and from organs back to the brain. Now what you see is a neuronal cell. Can you see that this cell collects a signal from left side and pass it through all along this cell to the right side? This is how a signal is traveled in a neuron. When a neuron passes these signals, there are very small electrical signals are produced. How one neuron passes a signal to another neuron? Okay, let's see. When a signal reaches down to the very end of one neuron, it releases chemicals called messengers to a tiny gap between two neurons. Do you see the bright yellow spots in this picture? Yes, they are the messengers. So these messengers go and bind to the next neuron. So the next neuron receives the signal. Neurons are constantly communicating with each other through electrical charges. Now you see is a big network of neurons passing a signal. So in healthy people, these neurons are working fine and they are quick and they automatically respond. When neurons don't work properly, problems can occur. When problems occur, it might lead to some diseases. Here are some diseases that caused by neuronal disorders such as chronic pain, and dementia, seizures, and movement disorders. My friend Gabby is going to talk about them in depth.
We just learned how the brain works, and now we're going to do a quick overview of two diseases that can happen in the brain: epilepsy and Parkinson's. Epilepsy is a brain disorder that causes seizures. A seizure is an uncontrolled electrical activity between the brain cells and can cause stiffness, twitching, or limpness. Parkinson's disease is a brain disorder that causes shaking, stiffness, difficulty walking, balance, and coordination. In some cases, for epilepsy and Parkinson's disease, medication can be used in order to control these diseases. However, in some cases, medication is not useful, and there's a technique called deep brain stimulation that can be used to help control the side effects of these diseases. Deep brain stimulation uses electrodes that are implanted in the brain and are connected to a small electrical device implanted in the chest. So these electrodes can help stop the movement-related symptoms such as the tremors, slowness in movement, and rigidity.
Now you learned about how our brain controls the body and the diseases due to unhealthy neuron communication and brain problems. So, can we treat these diseases? What do you think? Of course, technology is well advanced to develop devices that can implant in the brain and treat areas in the brain that cause problems. These devices consist of electrically conductive materials that comes into contact with brain cells. Electrically conductive materials can pass electrical currents. So, they can pass electrical signals to unhealthy or injured brain cells and restore their normal function. So, these implants are very small, so they can be implanted into your brain. And here we have shown some examples how they look like. To develop these implants, nowadays they use metals. They are very good conductors. They efficiently pass current, but they have some shortcomings. They are hard material, so inserting them into a soft tissue can cause damage. Also, some metals can release toxic compounds during the process. Obviously, these materials are not naturally present in our body, so they are not host-friendly materials. So with time, our body responds to reject these devices. So the device fails after some time. This picture shows an implant in a tissue, and after some time, body produces a protective cover around this device to reject it. But on the other hand, let's see carbon nanotubes. Carbon nanotubes are soft and flexible, so they're less likely to cause considerable damage during implantation. Also, carbon nanotubes are made from carbon atoms, so they are host-friendly and they do not release toxic compounds. In this picture, we have shown how a neuronal cell grows on a carbon nanotube film. See how compatible this cell on a carbon nanotube film. So carbon nanotubes shows better properties than metals. Also, when these implants are produced in small scale, carbon nanotubes show better properties than metals.
Chetney just told us about how carbon nanotubes are a good option in terms of working with our bodies. So now we're going to talk a little bit about electrical stimulation and show an external use of these CNT electrodes.
Now I'm going to show you how electrical stimulation actually works, and I'm going to use our own carbon nanotube electrodes for this experiment. So you can see these are our electrodes. I'll show you later how these electrodes are going to make. And this is the electrical stimulator that I'm going to use for this experiment.
When we start to make these carbon nanotube electrodes, we first have to embed 6 fibers into a polymer in order to hold the fibers where we want them. Chetney is going to use this sample as she shows you how she works through making the electrode.
Alright, now I'm going to show you how we make these electrodes in our lab. So In this polymer, we have set 6 carbon nanotube fibers inside of it, and then we slice it very thin so we can have these structures. So here we have carbon nanotube exposed in both sides, this side and the other side, so we can make an electrical connection to a wire from one side.
So this is what one of those cross sections look like in an illustration.
To make an electrical connection, I'm using this silver paint. So I'm going to use this silver paint to make an electrical connection to these carbon nanotube fibers using the silver paint and this wire.
So Chetney is going to take a little bit of silver paint and apply it to the back of the CNTs embedded in the polymer. And then she's going to take the copper wire and line it up over top of that silver paint and apply a little bit more paint on top of it in order to make sure that there's a good connection between the CNTs and the wire. Then Chetney is going to use epoxy, which is like a glue, in order to cover the back of the electrode where the wire has been attached so that no solution, no water from where we're going to be placing the electrodes or anything can interfere with that connection between the wire and the CNTs.
Okay, these are our carbon nanotube electrodes. You just learned how we are making this. So here I have embedded like 6 fibers in it. So there are 6 conductive contacts, and this is our stimulator. So basically what it does is it can generate electrical currents. So here we can control how strong we want to give these currents, and here how long we want to give it, and then the rate of these electrical pulses are given. These are our metal electrodes. So I'm going to put these electrodes under the nerve down here, which controls my pinky here. So we are using 2 electrodes, and now I'm going to make the connection with this electrical stimulator down here. So if you look at this setup, you see only the connection, the electrical connection to my nerves in my hand is through only the electrodes, like where it can pass current. Now what we are going to do is use the stimulator to pass current and try to control my arm. So we have kept the pulse width, which is like the duration of the pulse, around 150, and we have set the frequency more or like a speed around 70. Now he's going to change the current, the strength of the current over here. Okay, now you see the movement of my hand. So whatever the current passes through this reach my nerves, and that electrical current is passed through the electrode down there and make my muscle move. This is not me moving my muscle, but the stimulator.
So you just saw the metal electrodes and how that stimulated Chetney's arm. So now Chetney's attaching a CNT fiber disc electrode that has 6 CNT fibers embedded in it to my arm using double-sided tape. So she's going to hook the electrode up to the stimulator. So now Chetney is going to adjust the strength of the current in order to stimulate my arm so my pinky will move. So as she increases that current, you can see that my pinky starts to move on its own. So I'll adjust my angle so that you guys can see it better. But my pinky is just sort of flexing up and down, and that is due to the current flow through my arm from the stimulator. When you compare the size of a metal electrode to a CNT fiber disc electrode, you can see that the CNT fibers that are embedded in the polymer are a lot smaller than that metal electrode. When you're doing external stimulation like we saw with the arms, the size isn't a huge factor, but when you move to internal stimulation, such as that deep brain stimulation we talked about earlier, you want a smaller electrode. CNTs have the same properties as these metal electrodes and are capable of being made smaller, which is why they are such a great material to use for implants or electrical implants. Thanks for watching our video on biological applications of carbon nanotubes. I hope you learned something.